the last session, we have seen one of the application of uniform circular motion, that is vehicle moving along a curved horizontal road. At that time, there are some mistakes in that derivation. That is, that derivation should be like this. As you know that weight N is equal to mg. Here, the force of friction, that is the centrifugal force, balances the centrifugal force, that will be equal to Fs is equal to mr omega square, or it will be equal to mv square upon r. As you know that Fs upon N is equal to mr omega square upon mg, or it will be equal to mv square upon r upon mg. That means Fs upon N is equal to r omega square upon g, or it will be equal to v square upon rg. Here, as you know that radius r of the circular track, that remains constant. N is equal to mg is equal to constant. Therefore, as speed increases, the force of friction also increases, but it has certain limit. That means, as you know that Fs maximum, it will be equal to mu s into n, where mu s is the coefficient of static friction. And therefore, we can write it as Fs upon n, that is Fs maximum upon n is equal to mu s. And that will be equal to, that is Fs upon n is equal, from these two equations, Fs upon n is equal to v square upon rg, and Fs maximum upon n is equal to mu s. We can write mu s is equal to v square upon rg. That time the speed will be maximum, therefore we can write it will be equal to v square max. That means v max is equal to under root mu s into rg. The expression should be like this. Now we have also seen one of the application of uniform circular motion, that is, we have proved the expression for bank road, that is v is equal to under root rg tan theta. This expression v max is equal to under root rg tan theta. This expression we have proved. Here, while deriving this expression, we have not considered the air resistance and the force of friction. By neglecting these two forces, we have derived this equation. Here, while considering this equation, yet the forces acting on that vehicle, we have seen it will be equal to the normal reaction N, and that will be direct, it is perpendicular to the road surface, and another will be equal to, another force will be equal to the weight of that vehicle. Here, at that time, in both the cases, that is, there must be the resultant force act, and that will be n sin theta, which is directed toward the center of the circular track. Here, at every time, the speed of the vehicle should not be v max is equal to under root rg tan theta. That means that speed has certain limit. It may be increases or it may be decreases. And at that time, we have to consider the force of static friction. That means at that time, the limiting force of static friction helps us for a certain limit. If the speed is greater than this, that is, if speed is lower or speed is higher. Then we are going to see now the two cases. What happens if the lower speed limit, when a vehicle is banked along a curved road at lower speed limit and higher speed limit. First, we are going to see the bank road at lower speed limit. See here, this is the vehicle, vertical section of the vehicle, car moving along a curved bank road at an angle theta. Here, this is the normal reaction N, perpendicular to this is angle theta. Here it will be n cos theta. Here, weight of the vehicle that acts in the downward direction. Here it will be component n sin theta. Here, as we have seen, the force of friction in this case, at lower speed limit, the force of friction is along this angle of inclination. That means it is in this direction. This is the force of friction. In this case, this force of friction, that is dissolved. It has two components, that is its vertical component and horizontal component. Then at that time, its vertical component, you can see it will be equal to Fs sin theta, and its horizontal component, you can see it will be equal to Fs cos theta, where this is the angle theta here. Here this force of static friction that is directed along the inclination, but it is in the upward direction. At that time, here it is resolved into two components, Fs sine theta and Fs cos theta. Now here the Fs cos theta, that is the horizontal component of force of friction, is opposite, parallel and opposite to that of the n sine theta. That means n sine theta and Fs cos theta, they are parallel but they are directed in opposite directions. And these two forces that plays an important role in a centrifugal force. That means these two forces balances the centrifugal force. That is here from this diagram we can write the two equations. These two equations are very important. That is mg is equal to, we can write now, it will be equal to mg is equal to Fs sine theta plus n cos theta. Mg is equal to Fs sine theta plus m cos theta. And another equation you can write, it will be equal to here mv1 square upon r. This is the centripetal force, and that will be equal to n sine theta minus Fs cos theta. This first case we have to see here for a speed v1 is less than under root rg tan theta. That means you can say that the speed is less. That means you can say that mv1 square upon r is less than n sine theta. That means this resultant force n sine theta is greater than that of this centripetal force mv1 square upon r. And at that time, force of static friction is along the angle of inclination and it is directed in the upward. These two equations are, so if the question is on the diagram, based on the diagram, you have to consider the diagram, and the diagram plays a very important role. With the help of that diagram, you can write the equations and you have to solve that equations. These two equations, we can write this mg, that will be equal to f sine theta minus plus n cos theta, and here these two forces n sine theta and Fs cos theta, that plays an important role to produce the necessary centripetal force. That two forces balances the centrifugal force, and therefore we can write this as mv1 square upon r is equal to n sine theta minus Fs cos theta. Now suppose this is your equation, this is equation 1 and this is your equation 2. If we divide equation 2 by 1, then you get this gets cancelled, then v1 square upon rg, and that will be equal to n sine theta minus Fs cos theta upon Fs sine theta plus n cos theta. Now here, as you know that this force of friction, that is equal to, you know that maximum limit, it will be equal to mu s into n, where mu s is the coefficient of friction. This you can write it as v1 square upon rg. Instead of this Fs, we can write mu s into n, that is n sine theta. If we divide it by n cos theta, we have to divide n cos theta to hold this equation, that is Fs is equal to mu s into n cos theta upon, it will be equal to n cos theta divided by n sine, that is Fs, again it will be mu s n sine theta upon n cos theta plus n cos theta upon n cos theta. Here you get v1 square upon rg is equal to n sine theta, sin n gets cancelled, sine theta upon cos theta, tan theta minus n cos theta, that will be equal to mu s upon mu s into tan theta plus 1. That is equation, you can write it as v1 square is equal to rg into tan theta minus mu s upon mu s tan theta plus 1. This is the equation. This equation we can write, that is v1 is equal to under root rg in tan theta minus mu s upon mu s tan theta plus 1. Here, this is the expression for lower speed limit. That is, see again with the help of diagram, you have to remember this diagram is very important. With the help of this diagram, you can write two equations, that is mg, that balances the two forces. We can write it to be Fs sine theta plus n cos theta. These two forces, Fs cos theta and sine theta, that balances the, that two forces are necessary for centripetal force, which balances the centrifugal force. Therefore, it will be mv1 square upon r is equal to n sine theta minus Fs cos theta, because they are parallel and opposite to each other. If we divide equation 2 by 1, then you get this equation. Here, as you know that force of friction is equal to mu s into n, where mu s is the coefficient of friction between tires of the vehicle and that of the road surface. We have to substitute the value of Fs equal to mu s into n in this equation, and if we divide n cos theta to whole these terms, then you get this equation here. Then you get v1 square upon rg is equal to tan theta minus mu s upon mu s tan theta plus 1. That means v1 square is equal to rg into tan theta minus mu s upon mu s tan theta plus 1. You have to remember this equation. Here we can write this equation as v1 is equal to under root rg into tan theta minus mu s upon mu s tan theta plus 1. This is the expression for lower speed limit. That means v1 is equal to under root rg tan theta minus mu s upon mu s tan theta plus 1. If mu s is greater than or equal to tan theta, then what happens at that time? V minimum, you can say it will be equal to V minimum is equal to 0. Mu s is greater than or equal to tan theta, then at that time you can say it will V minimum is equal to 0. And this is true for most of the rough roads for which that roads are banked at a smaller angle. Here that is V minimum is equal to 0. As we have seen, this is possible only for the this is possible on most of the rough roads where the angle of banking is very small. Now we have to find out an expression for this is we have seen lower speed limit. Now we are going to find out an expression for upper speed limit. Then at that time also here vehicle that is here moving along. In this case we have to see with the help of this diagram. We can show again here. For upper speed limits, that means m v2 square upon r. That will be the centripetal force. That is v2 is greater than or equal to under root rg tan theta. That means m v2 square upon r is greater than or equal to n sin theta. That means n sin theta that is less than the centripetal force m v2 square upon r. Then at that time the force of friction is directed with the help of this diagram. See again here. This vehicle is banked at an angle theta. Here, this is the normal reaction n. Here again it will be n cos theta. This is angle theta. Here it will be n sin theta. Now here this force of friction, if for upper speed limit the force of friction that is along the angle of inclination, that is along inclination, but it is directed in the downward direction. And this can be resolved into two components. Its horizontal component you can say it will be equal to Fs cos theta and another will be equal to Fs sin theta. Here you know that it will be the weight mg that of the vehicle. Now with the help of this diagram we can write the two equations here also. Now weight mg you can write it will be equal to mg is equal to now n cos theta minus Fs sin theta. This equation you can write. Here you have to see in case of lower speed limit and what happens in case of higher speed limit, that is mg is equal to n cos theta minus Fs sin theta, and these two forces that is n sin theta it is directed toward the center, and n sin theta F cos theta that plays an important role for centripetal force. These two forces are parallel to each other and therefore that decides the necessary centripetal force which balances the centrifugal force, and therefore you can write it as mv2 square upon r is equal to n sin theta plus Fs cos theta. This is your equation 1. Again, this is your equation 2. In this case, if we divide this equation 2 by 1 again, then you get V2 square upon Rg is equal to, again, n sine theta upon n sine theta plus, instead of Fs, you can write mu s into n cos theta upon n cos theta minus Fs, and that will be equal to mu s into n sine theta. Again, if we divide this, V2 square upon Rg is equal to n sine theta upon n cos theta plus mu s into n cos theta upon n cos theta divided by the whole this, that is n cos theta upon n cos theta minus mu s n sine theta upon n cos theta. Then in this equation you get V2 square is equal to Rg into tan theta, sin theta upon cos theta, that will be equal to tan theta plus mu s, n cos theta gets cancelled, divided by, here also this gets cancelled, that means 1 minus mu s tan theta. Here V2 square is equal to Rg into tan theta plus mu s upon 1 minus mu s tan theta. This, if we write, it is. Now, you understood this equation. Now, we can rough this. It should be remembered that when the question is asked on the diagram is very important. With the help of this diagram, we can write these two equations. And when you write these two equations, then we can solve the further equation easily. Therefore, you have to write these two equations. Now, see here, weight mg, that is the n cos theta minus fs sin theta. They are in opposite directions. Therefore, that balanced by this mg. Now here, these two forces, Fs cos theta and sin theta, they are parallel, they are in the same direction. They provide the necessary centripetal force, which balances the centrifugal force. Therefore, mv2 square upon r is equal to n sin theta plus Fs cos theta. This Fs we can write it as mu s into n. And if we substitute that mu s into n and divide the whole equation by n cos theta, then you get this equation. That is V2 is equal to, we can write, it will be V2 is equal to under root of, that is, you can say minimum, it will be maximum, is equal to under root Rg into tan theta plus mu s upon 1 minus mu s tan theta. This is an expression for upper speed limit. In this case, if mu s is equal to cos theta, if mu s is equal to cos theta, then at that time you can say that V2 max, and that will be equal to infinity. But you can say that mu s max is equal to 1. Mu x max is equal to 1. What happens here? If mu s is equal to cos theta, then at that time you can write V2 maximum is equal to infinity and mu s is equal to, but it will be mu s maximum, and that will be equal to 1. That is, for an angle theta is greater than or equal to 45 degree, you can say that V2 will be equal to, for an angle theta is greater than or equal to 45 degree, V max is equal to infinity. V maximum is equal to infinity. And therefore you can say that here the maximum speed will be equal to infinity in this case. However, for heavily banked road, minimum limit may be important. For heavily banked road, we have to consider the minimum speed limit also. These are the two cases which we have seen. That is, the speed never be V maximum is equal to under root Rg tan theta. What happens if the speed is greater than that and speed is less than that? That we have seen the two expressions, that is the lower speed limit and upper speed limit. Then in these two equations we have seen, that is the expression for lower speed limit and upper speed limit. Last will be at that time, if we substitute mu s is equal to 0, that means we have not considered the mu s. That means the force of friction between tires of the coefficient of friction between tires of the vehicle and that of the road surface. If we neglect that, then the expression will be V is equal to under root Rg tan theta. And this is the safest speed. That means you can say that this is the safest speed if we not consider the mu s. In this way, we have considered the applications of uniform circular motion, and that applications we have seen it will be, first will be, we have seen vehicle moving along a curved horizontal road, Another will be vehicle moving, as we have seen the wall of death. And another example, we have seen the banking of roads. On that there will be the definition of banking of road, necessity of banking of roads, expression for banking of road without considering the forces acting on that. That will be the force of friction and the air resistance. By neglecting that, we have find out v is equal to under root rg tan theta. That is the maximum speed limit, but that speed never remains as it is. It may be increases or it may be decreases, and that is the fs helps us to decide that speed limit. That is, if the speed limit is greater than this or lower than this, then what happens? That conditions we have seen. And last will be, if mu s is equal to 0, then the surface speed, we can say it will be equal to v is equal to under root rg tan theta. Now we are going to see the another derivation, and that derivation is for conical pendulum. That conical pendulum, we have to see here the expression for conical pendulum we are going to see now. Here, what is meant by simple pendulum? A heavy particle. Simple pendulum will be a heavy particle suspended by weightless, inextensible string from the fixed rigid support. That means a point mass, or you can say that a bob that is suspended by a weightless, inextensible, flexible and twistless string from the fixed rigid support. That is called as simple pendulum. Like this is the simple pendulum, and the simple pendulum has given a motion in such a way that the string is in the same plane. Then that is called as a simple pendulum. This simple pendulum has given a motion in such a way that pendulum performs the cone. That is, that pendulum moves, or the simple pendulum has given a motion in such a way that performs a horizontal circle and string forms a cone. That is called as conical pendulum. What is the definition of conical pendulum? The definition of conical pendulum is that the simple pendulum has given a motion in such a way that the bob performs the horizontal circle and string forms a cone. Then that is called as conical pendulum. Now here, the vertical section of that conical pendulum is shown in this diagram. With the help of this diagram, we are going to see now, or we have to derive the expression for period of conical pendulum. Now here, bob performs the horizontal circle and the string forms here. The string forms a cone. The shape of this pendulum is like a cone, therefore it is called as conical pendulum. Here, this is the center. Here you can say this is the rigid support A. Here, this is the height of conical pendulum. This is the length of conical pendulum. Now see here, this is bob, omega. Bob moves with the angular velocity omega. Here it will be the radius r of this horizontal circle. Suppose you can say this is a point B, this is point C. Here, at this is the vertical section of this conical pendulum. At this point B, as the bob performs the horizontal circle and string forms a cone. Here, theta be the semi-vertical angle of the cone. At this point B now, the forces acting with the help of this diagram shows the vertical section of a conical pendulum of a bob having mass m and length L. Here, at this point B, the forces acting at the position B, forces acting on this bob are its weight mg that acts in the downward direction. And another force is the tension along the string, that is T0, that is directed towards the point A, or it is towards the rigid support. These two forces acting on this. Here you can say that this resultant force, as the bob performs the horizontal circle, that means you can say that the resultant force must be in the horizontal direction and it is directed toward the center of the circle, which provides the necessary centripetal force for this horizontal circular motion. Here, at that time, all the vertical component or all the vertical forces cancels with each other. Now here, this tension T0 can be resolved into two components. Its vertical component T0 cos theta, and here another component will be equal to T0 sin theta, and this is directed toward the center of this circle. Here, this T0 sine theta, that is necessary for the centripetal force, which is the resultant force, which balances the centrifugal force. Now, with the help of this, we can write the two expressions. Now, here, this is L, this is H. Now, here, H is equal to this, H is equal to cos theta is equal to H upon L. Therefore, you can write H is equal to L cos theta. And sin theta is equal to this R upon L. Therefore, R is equal to L sin theta. That is the radius of this horizontal circle. Now, from this diagram, we can write these two equations. That is T cos theta. Here, T cos theta is equal to mg. And the another equation, that is this T0 sine theta, that is the component is T0 sine theta, that balance the that is necessary for centripetal force, and it will be equal to mr omega square or mv square upon r. That is T0 sine theta is equal to mr omega square and T0 cos theta. This is second equation. You can write T0 cos theta is equal to mg. This is our equation 1. This is our equation number 2. If we divide this equation 1 by equation 2, then you get sine theta. T0 gets cancelled. Sine theta upon cos theta is equal to r omega square upon g. That means omega square is equal to g sine theta upon omega square is equal to g sine theta upon r cos theta, where omega is the angular velocity. See here, with the help of this, I have to rub this diagram for that purpose. See again here, this is the vertical section of a conical pendulum of a bob having mass m and length L. Here, h is the height of that conical pendulum, that will be equal to L cos theta, and r be the radius, and that will be equal to L sin theta. Here, the tension T can be resolved into two components. Vertical component T cos theta, horizontal component T0 sin theta, and that's T0 sin theta that is necessary to provide the centrifugal force for the horizontal circular motion. With the help of this, we can write these two equations. T0 sin theta is equal to mr omega square, and T0 cos theta balances the weight of the bob, and that will be equal to mg. Then from these two equations, we can write sin theta upon cos theta is equal to r omega square upon g. That means omega square is equal to g sin theta upon r cos theta. We want to find out an expression for period of conical pendulum. For that purpose, you know that the relationship between angular velocity and period, we know that it will be equal to omega is equal to 2 pi by t. That means as omega square is equal to g sin theta upon r cos theta, omega is equal to under root g sin theta upon r cos theta. As omega is equal to 2 pi by t, that means 2 pi by t is equal to under root g sin theta upon r. R, we have seen that radius r is equal to L sin theta. That is the radius of the circle, and that you can write it will be equal to r. It is L sin theta, and this cos theta remains as it is. That means 2 pi upon t is equal to under root g upon L cos theta. This is omega. Omega is equal to 2 pi by t, and that will be equal to under root g upon L cos theta. And that is t is equal to period of that conical pendulum. You can write it will be equal to t is equal to 2 pi under root. This will be, you can write it will be equal to 1 upon 2 pi. You can write it will be equal to 1 upon, that is period of conical pendulum. You can write it will be equal to t, and that t is equal to 2 pi under root L cos theta upon g. In this way, we can derive an expression for period of conical pendulum, that is t is equal to 2 pi under root L cos theta upon g. Here, question can be asked on this topic. The frequency you can find, frequency n is equal to 1 upon t. You can write it will be equal to 1 upon t, that means 1 upon 2 pi under root g upon L cos theta. That is an expression for n. You can write it will be equal to 1 upon 2 pi under root g upon L cos theta. Sometimes question can be asked like this. With the help of diagram, that is define conical pendulum and obtain an expression for period of conical pendulum, that expression, while at that time you have to prove this equation t is equal to 2 pi under root L cos theta upon g. Here, in this way, we can derive the expression for the period of conical pendulum. Up to this we have studied. Now in the next session we are going to see the different tensions, that is vertical circular motion we are going to see now. Before that, students, I have to say something to you, that is, if there are certain mistakes in these videos, there may be mistakes, then with the help of book, follow the book and understood that concept. There may be possibility of some mistakes. Go through the book and clear that mistakes. This is my small effort to reach towards you. So, thank you.